Hello, everyone. Today we are going to talk about hyperbolic functions. Hyperbolic functions are special artificial functions which we need in math sometimes to express our answers more convenient. Sometimes they're just like easier to use when you solve problems or do integrals. Uh, we are not going to use hyperbolic functions to solve any problems in class this semester, but some other classes can use them like differential equations. You can see them. Maybe you are going to see them if you did not do linear algebra. So you will need to know how hyperbolic functions look and kind of recognize them when you see them and don't be scared of them. Because of that, I'm not going to go very deeply into hyperbolic functions and consider lots of examples. I'm going to just do introduction and kind of go around hyperbolic functions. We are going to start with definitions. Definitions are like how we design these functions. I'm going to define first three hyperbolic functions. First one is going to be sine hyperbolic of x. You'll probably ask me, why sine hyperbolic? Why don't we call it like a different word hyperbolic? We are going to kind of explain it a little bit later. For right now, guys, let's look at the definition of hyperbolic sine. You see that actually hyperbolic sine is just the difference of two exponential functions, one with positive exponent and one is negative exponent, and divided over 2. So basically that's not a new function. If hyperbolic functions disappear from math, nothing is going to happen. But you are going to see that sometimes they are very convenient, especially in integrals. Okay, next hyperbolic function is going to be cosine hyperbolic. And it's going to be very similar to sine. The only difference is going to be plus between exponential functions. And the last hyperbolic function is going to be tangent. Sorry, my end didn't look very nice. Write down tangent one more time. And tangent hyperbolic is going to be defined through sine and cosine hyperbolic as normal tangent. So we're going to say that tangent hyperbolic, it's a sine hyperbolic over cosine hyperbolic. And this is going to be the first similarity between hyperbolic functions and trigonometric functions sine and cosine. You see the tangent hyperbolic is defined as a ratio between sine and cosine. There are going to be more similarities, and that's majorly why people call them like sine, cosine, and tangent hyperbolic. And I'm sorry, I forgot to put a little h over here. Well, besides sine, cosine, and tangent are defined this way. How the graphs are going to look. Again, I'm going to do very briefly graphs of all three functions and explain as much as possible. And if you are interested in more details, you can always look up in the book. I'm going to start with sine hyperbolic. Now, guys, I'm not going to explain a lot what is going to happen here, but you probably see that when x equals to 0, we are going to have 1 minus 1, which is 0 over 2, and we are going to get a point 0 here, right? Now, if you plug in over here around this function, something large, like big axis or axis going to infinity, how the function is going to behave? Well, we know that e to the power of negative x at infinity goes to 0. So basically, guys, we are going to have our function looking very much as e to the power of x over 2. If you still remember how exponential function looks, it's going to be a rapidly growing function. We just need to divide over 2. Well, because I don't have any good scale on my graph, I'm just going to maybe graph in dashed line e to the power of x over 2, like this. And then start bringing my graph to it, like close to it. Maybe I should use a different color to do the graph of the sine, right? So my sine is going to approach actually e to the power of x over 2 on positive end and go through 0, something like this. What is going to happen when x goes to negative infinity. Very large negative x is going to turn my first term into 0, because it's going to be e to the large negative power. But this term was going to be a very large term, and it's because it has minus already, and it's going to have one more minus from all these negative x's. It's going to behave like exponent, just normal growing positive exponent. Besides the fact that it's going to have minus in front means that it's going to be flipped over a x-axis. I'm going to graph how it's going to look. So I'm going to maybe label my dashed lines. This one is e to the power of x over 2, and this one is negative e to the power of negative x over 2. And my graph is going to approach this line at infinity. And for exponential function, infinity happens very, very fast because function grows a lot. Well, generally speaking, the graph must be more symmetrical, but that's how graph is going to look. It's going to look like a cubic parabola. The only difference is the cubic parabola is growing much, much slower than a hyperbolic sine. Okay, I'm going to label this is a graph of sine hyperbolic of x. Okay, and let's move to the next graph, which is going to be cosine hyperbolic of x. And let me go back maybe to the blue color. So for cosine, guys, because we are going to deal with very same exponents, it's going to be a little bit easier for me to graph. So the only difference here is going to be that at positive infinity, it's still going to be the same, similarly looking e to the power of x over 2. But here, because we do have plus, my second exponent is not going to be below x-axis, but it's going to be above x-axis. My second exponent, which is going to be at negative infinity, is going to be e to the power of negative x over 2. And the number here is positive. What is going to happen at 0? If you plug in 0 here, you are going to get what? 0 here, e to the power of 0 is 1, e to the power of minus 0 is also 1, 1 plus 1 is 2, divided over 2 is 1. So the point is going to be 0.1. Let me label x and y. And I'm going to use the red color to graph the function. Yeah, actually my scale is not really 1 here because, well, if I plug in 0 over here, I'm going to have what? 1 over 2. So this point is actually 1 over 2. So my point 1 is actually over here. Sorry. So I'm going to graph. Cosine looks very much like what? Quadratic parabola, but growing much, much faster. The last one we'll need to graph is going to be tangent. And to do that, I'll probably write down tangent through exponential functions to kind of show it better a little bit, like how the graph is going to look, or explain it a little bit better. Forgot to plug in 0. Here, guys, it's also 1/2 here, not 1, because the function is like e to the power of x over 2. Over 2 means that it will go through 1/2. And this is 1 over here. Okay, let me move to tangent. Before I move to tangent, I'm going to continue over here and write down what is sine. It's e to the power of x, sorry, minus e to the power of negative x, and it's supposed to be over 2. Now, cosine is going to be e to the power of x plus e to the power of negative x, and also over 2, because it's in denominator, it's going to jump into numerator. Basically, guys, these 2's are going to just cancel, and we are going to have just ratio of difference of two exponents and the sum of two exponents. How it's going to affect my graph? My straight line that looks straight. Let me make it more straight. Okay, so that's going to be x, that's going to be y. Well, maybe I should talk about a 0 point first. What is going to happen when x is equal to 0? When x is equal to 0, I'm going to have 1 here and 1 here, right? And 1 minus 1 is 0. So no matter what is in denominator, unless it's 0, we are going to have 0 point over here. So at 0, it equals to 0. Now, what happens at positive infinity? Positive infinity, large x's. So e to the power of negative x goes to 0, e to the power of negative x goes to 0, and we have e to the power of x over e to the power of x, which is going to go to 1, right? So my graph is going to have, oh, well, I'm supposed to use a blue color to do like asymptotes. It's going to have a horizontal asymptote. Here, guys, I'm going to make a scale up to here just because if I do one square for 1 unit, my graph is going to be very, very slim. So I'm going to graph what happens to tangent around positive axis, something like this. Now, around negative axis, what are we going to have? When x are negative, the first term in numerator and first term in denominator are going to disappear because it's going to be very, very small number, right? And over here, we are going to have two large numbers, basically two same numbers, right? The only difference is that it has a minus in front. So instead of 1, we are going to get -1 because exponential functions are going to cancel and we are going to have -1 as a limit. And if I kind of keep my old scale, it's going to be -1 here. And that's going to be asymptotic behavior near infinity. Look, tangent hyperbolic looks a lot like arctangent, right? Well, arctangent has power 2 here, I guess, difference and a slightly different behavior nearby 1, but still, you can kind of use it as mnemonic rule to memorize how they look. Okay, graphs of these three functions don't look at all like trigonometric functions, right? But behavior of these functions is going to remind you about trigonometric functions. Before we move to that behavior, I want to label each of these three functions with 1-to-1 or not 1-to-1. And first, I'm going to label them with their names because I labeled sine and did not label tangent or cosine. So guys, first function, if you draw a horizontal line anywhere, it's going to intersect it only once, right? So like intersecting only once, 1-to-1. The second one intersects 2 times, not 1-to-1, not 1-to-1. And the third one intersects only once, 1-to-1. Why do I need to know that? Well, because always I think about inverses. And for this one, there is inverse, and inverse is sine hyperbolic inverse. You can write down arc sine hyperbolic inverse, but arc sine hyperbolic, but usually people are not going to do this. For tangent, kind of inverse is going to be tangent hyperbolic inverse, right? What to do with cosine? Well, remember when your function does not have inverse because it's not 1-to-1, we can kind of find part of the function which is 1-to-1 and has inverse. In our case, guys, we can consider this branch, like the branch with x greater or equal than 0, and this branch is going to have inverse, and inverse in our case is going to be cosine hyperbolic inverse of x. So, well, we see that all three functions do have inverses. The cosine has kind of limited range and as a consequence, it's a limited domain of like inverse function. Okay. Now, let's talk about some identities which are like connecting these functions and why actually we call them like hyperbolic trigonometric functions. I'm going to start with maybe a differentiation. So I'm going to differentiate sine. Okay. And how I'm going to differentiate it? Well, I'm just going to use a definition and differentiate. Derivatives. So I know that sine hyperbolic of x is e to the power of x minus e to the power of negative x over 2. Now, if I differentiate it, what I'm going to have, what is going to be the derivative of hyperbolic sine? Well, let's differentiate it. E to the power of x, we know the derivative is still e to the power of x minus, and e to the power of negative x derivative is e to the power of negative x. But when we differentiate negative x, we are going to get -1 in front, and that's going to give us like a second minus over here. Then we copy over 2 because it's a constant. And if we simplify this expression, we are going to have e to the power of x plus e to the power of -x over 2. If we scroll back up, we are going to see that derivative of this sine is actually equal to cosine hyperbolic. You see the similarity. So actually, this is cosine hyperbolic of x. This is one of the first similarities here, right? Remember that derivative of sine is equal to cosine. Now, let's calculate derivative of the cosine hyperbolic and see like if we can hold the identity another like side of this. So we have e to the power of x plus e to the power of -x and divided over 2 and derivative. Same way, I'm going to differentiate e to the power of x. Here, guys, e to the power of -x is going to be the derivative, and this minus comes because I differentiate this -x over 2. And maybe I don't need to scroll up back because you actually can see that this is nothing else than just sine hyperbolic of x. If you guys recall, the derivative of cosine is not really sine, it's minus sine, right? So here is the difference. You cannot invent a different function which has all the same properties of the function you already have. So, for example, if you invent a sine hyperbolic, but this sine hyperbolic has the very same properties of normal sine, that it's not a new function, that's the same function sine named by sine hyperbolic. So we are going to see some differences between hyperbolic functions. Well, we already seen the graphs are different, but also like differentiation also going to give us different results. What else? Well, guys, you can probably differentiate tangent at home. Well, that's a special kind of problem. And I'm going to move to some other identities. Well, I'm going to do more identities. I'm going to write down more identities. More identities. More identities. For example, what is sine hyperbolic of -x? Remember that sine of -x, because it's an odd function, is going to be equal minus sine of x. Is this going to be the same with hyperbolic functions? Well, let's just plug in e to the power of, supposed to be x, but if I put -x instead of argument, I'm going to have -x minus e to the power of minus -x. What I did, I just plugged in -x instead of x into definition of sine. And I'm going to get e to the power of -x minus e to the power of x over 2. It's not exactly sine. Sine is supposed to have positive term and then minus negative. But if I put this minus kind of outside of the fraction, I'm going to get e to the power of x minus e to the power of -x over 2. So actually, sine of -x is equal minus sine hyperbolic of x. So for sine, the same identities work. We can look at the graph and see that, yeah, well, sine is actually odd function. How about cosine? Well, cosine is even function, we see it, and we are going to just, without even checking, assume that cosine of -x is going to be equal cosine of positive x. So here, because it's even function, right? What can we tell about tangent? Again, I don't want to do calculations again, but you see that tangent is symmetrical odd function. So we are going to have a minus jumping outside of the function because it's odd function. And we are going to have the same identity as for normal trigonometric functions. Very good. Two more identities, and that's going to be basically it. We can move to integrals. Two more identities. So that's just like I checked the one identity. I'm going to check another identity. Yeah, guys, my next identity is going to be Pythagorean identity. Remember that for real trigonometry, Pythagorean identity sounds like this. Cosine square of x plus sine square of x equals to 1, right? Yeah, unfortunately for hyperbolic functions, identity is going to look slightly different. Well, because I'm a teacher and I know this identity already, I'm going to set it correct way. Cosine hyperbolic. Guys, how about I write down instead of cosine CH hyperbolic square of x plus, oh, sorry, plus minus minus. Why I'm not getting back the drawing? Hey, come on. I did something wrong with my pen and it's stopped working. Give me a second, please. Oh, okay. Return back. Sine hyperbolic equals to 1. You see that my Pythagorean identity here looks slightly different. Instead of plus, it has minus. But you remember that if everything is identical for a new set of functions, then, well, it's just a different name for the same set of functions. So supposed to be some differences. We do have some similarities, and that's why we call them sine and cosine hyperbolic, but we are supposed to have some differences. I'm going to prove this identity, and please watch how I do this. I'm going to use definition again. Definition means that I'm going to actually express each sine and cosine through the exponential function. Okay? And let's do it. So cosine is going to be what? E to the power of x plus e to the power of negative x over 2 squared minus e to the power of x minus e to the power of negative x over 2 squared. And kind of, I'm supposed to check whether it's 1 or not, because it's kind of, I'm trying to verify identity, right? What I'm going to do, guys, I'm going to square actually, like use a formula a plus b squared, right? And this over 2, when we square it, is going to give me over 4, right? So I have a squared e to the power of x squared plus 2ab e to the power of x e to the power of negative x and plus b squared, right? Plus e to the power of negative x squared. Continue minus, well, denominator is 4 again because 2 squared is 4. And I'm going to use the same formula, just minus in front. So I'm going to make it much quicker. That's going to be minus because of this minus, right? 2e to the power of x, e to the power of negative x, and plus e to the power of negative x squared. And we are checking whether it equals to 1 or not equal to 1. Well, what I'm going to do, guys, I'm going to simplify this expression next way. I know that when I raise power to the power, it's going to be just a product of two powers, right? So I'm going to write down 2x instead of x to the power of 2. Here, guys, when I have a same base, I can actually, same base means that it's e to the power of x, e to the power of negative x. I can actually add the powers. In our case, I'm going to subtract them just because actually there is a minus, right? X minus x is going to give me 0. E to the power of 0 is going to give me 1. Sorry, I don't have any like big space over here to write it down. And that's e to the power of 0 is going to give me 1. So I'm going to have plus 2. On this side, it's going to be e to the power of negative 2x, right? Minus x by 2 negative 2x. Still divided over 4 minus e to the power of 2x. Same way, it's going to give me 1 and plus e to the power of negative 2x and divided over 4. Sorry, my handwriting is not very good, but that's because I keep my screen vertical. When I make it horizontal, I keep pressing something on the screen and it gets frozen. So now, guys, because I do have a same denominator everywhere, right? I'm going to just kind of unify it into one fraction over 4. And I have e to the power of 2x plus 2 plus e to the power of negative 2x minus. This minus is going to be distributed to every term here in this fraction. So minus e to the power of 2x minus and minus plus 2, and minus and plus is going to give me minus e to the power of negative 2x. Now, guys, if we kind of look carefully, we are going to see that e to the power of 2x and e to the power of 2x. This was minus, same happens with this, and we just have 2 plus 2, which is actually equal to 4, right? So we are actually having 4 over 4, which is equal to 1. So we proved our identity, and that means that Pythagorean identity is going to look different for functions. There's a minus between, so cosine hyperbolic minus sine hyperbolic. There are more identities. We are not going to kind of go over each of them. Let me kind of talk a little bit about integration and then move to inverse functions. So, well, integration, integrals. We know that sine hyperbolic of x derivative equals cosine hyperbolic of x. Now, guys, if we integrate cosine hyperbolic of x dx, we are going to get sine hyperbolic of x plus a constant, right? Kind of easy. Here, guys, no worries about minuses because hyperbolic functions don't have this tricky minus in front when you integrate opposite. So what is going to be integral of sine hyperbolic of x dx? Well, because derivative of cosine was equal to sine, so sine is going to give us cosine. So here we have a perfect symmetry between integrals. Uh, what else? I think we can go to inverse hyperbolic functions. Uh, I even don't know. Maybe I should do inverse hyperbolic functions. Mostly, guys, we're not gonna use just inverse hyperbolic functions. Mostly, guys, we will need to know what are derivatives of these inverse hyperbolic functions. So maybe I'm going to talk about that. Inverse hyperbolic functions. And let's go over inverse. So we do have three inverses, right? Sine, hyperbolic, inverse, cosine, hyperbolic, inverse. Works only for x rhetorical than 0, right? Or actually, it's supposed to be greater or equal than 1 because we are kind of doing x here. Sorry, I placed 0. But, okay. And uh, tangent hyperbolic, tangent hyperbolic inverse. That's why it's 1, not 0. Well, x is going to be kind of from 0 to infinity, right? But inverse function actually is going to have argument as y. And y, if you go back to the graph of cosine, is going to be like from 1 to infinity. So there are three inverses, right? What I'm going to do, guys, I'm going to consider a derivative of sine hyperbolic inverse. Okay? And well, there is no other way except I'm going to prove it, I guess. So let's differentiate. I'm going to write down derivative of sine hyperbolic inverse. And the question mark, what is derivative of sine hyperbolic inverse? Let's write down that sine y equals sine hyperbolic inverse of x, right? As usually, we can take sine hyperbolic from both sides. Sine is 1 to 1, sine hyperbolic is 1 to 1 function, so we can do that. So we are going to take sine hyperbolic here. And here, guys, sine hyperbolic and sine hyperbolic inverse are going to cancel each other, and we're just going to get x argument. Then, what we're going to do? We are going to differentiate this nice expression. We do know that derivative of sine hyperbolic is just cosine hyperbolic, right? Then we need to differentiate y, which is going to give us y prime. Remember our standard way of proving. And here is going to be 1. Now we can calculate our derivative of function y, which is actually sine hyperbolic inverse. And that's going to be 1 over cosine hyperbolic of y, right? Very good. But usually we like to have a function of x here, right? As we did with sine and cosine inverses, we are going to use Pythagorean identity here. Remember, I just proved identity that cosine hyperbolic square of x minus sine hyperbolic square of x equals to 1. So what is going to be cosine hyperbolic then? Cosine hyperbolic square of x equals 1 minus sine hyperbolic square of x, right? And if I extract the square root of both sides, I'm going to get that cosine hyperbolic square without square already. Sorry. Move it a little bit up. cosine hyperbolic of x is just going to be a square root of 1 minus sine hyperbolic square root. So I'm going to apply it over here. Instead of x, I'm going to have y here because my x actually is y, right? Yes, my argument is y. I'm going to write down 1 over a square root of 1. Why did I put minus here? I think I just followed Pythagorean identity. If I move this sign over here, I'm supposed to have plus. Sorry. Plus sine hyperbolic square of y, because my argument here is y. Now, guys, because y is not my original argument is x, I know that y actually equals sine hyperbolic inverse. So I'm going to plug it in instead of y. I'm going to use this and plug it instead of y. So what I'm going to have, 1 divided over 1 plus sine hyperbolic, scroll a little bit up, of sine hyperbolic inverse of x. And then I'm going to square all this expression because there is a square of this function, right? I want to copy new line. I'm just going to kind of remind you that sine hyperbolic of sine hyperbolic inverse cancel each other, and I'm just going to have x here. And when I square it, I'm going to have a very nice short expression, 1 plus x squared. You see? If you recall what was derivative of sine inverse, arcsine, you probably remember that. Write it down. Sine inverse of x derivative was equal 1 over 1 minus x squared. And here we have plus. So actually, kind of very similar formula, just instead of minus, we do have plus. Well, usually, guys, we are going to use this formula when we do integrals. So if derivative of, now we have a formula, right? Sine hyperbolic inverse of x derivative, because that was my y actually, y prime, is equal 1 over 1 plus x squared. Here we found y prime, right? Here we found y prime. And y actually was sine hyperbolic inverse. So y prime was derivative of that. If sine hyperbolic inverse derivative equals to that square root, then integral dx over 1 plus x squared is going to be equal what? Sine hyperbolic inverse of x plus a constant, of course, antiderivative. So guys, we added one more integral in our kind of list of known integrals which we can calculate, and this one. In future, guys, when we start next chapter, I'm going to teach you how to calculate this integral different way. But for now, you can use this formula to calculate the integral. In future, we are going to learn another formula which is not going to use any hyperbolic functions. Well, basically, guys, that's all I wanted to tell about hyperbolic functions. Maybe I'll give you one more derivative, or maybe I'll give it as a problem. So as usual, at the end of the section, I'm going to put some problems for you to practice. Okay, let's do it. Let me scroll it up. Practice. Let me change my color, like blue. We're going to start with problem 1. How about, guys, finding tangent inverse hyperbolic derivative? What is it? Same way we did sine inverse. Right. So problem 2. I'm going to just give you some problems to differentiate or integrate using kind of some formulas. So let's say differentiate a y equals sine hyperbolic of x. be y equals sine hyperbolic inverse of square root of x. And there's supposed to be square root of x here too, because otherwise it's just a formula which we already know. So it's kind of composition with something which we already know, right? What else? Maybe, guys, you can prove identity. I'm going to write it down. And that's going to be the last problem. Prove identity. Oh, guys, I'm going to write down a set of sine and cosine, just S and C, because otherwise this identity is going to look super long. But you understand that that's actually that it's sine hyperbolic. And when it starts with C, it's a cosine hyperbolic. Sorry, to make it looking shorter. You guys probably remember somewhere in trigonometry we had an identity that sine of alpha plus beta or sine of x plus y, and that was equal sine of x by cosine of y plus cosine of x by sine of y, right? Is similar identity going to work for hyperbolic functions? How would you prove this, guys? To prove this, you will need to use definition of sine hyperbolic and cosine hyperbolic definition through exponential function. Okay? I think that's all because we did not learn much about like how to deal with hyperbolic functions or examples on them. So one proof that's going to be proof. Couple of problems to differentiate compositions and one problem of identity. We also have expression for inverse hyperbolic functions through normal functions, but I think probably that's just going to be too much for this section. Okay, so guys, try all these 4 problems, 1, 2, 3, 4, before Wednesday, and on Wednesday we are going to discuss them. Okay. Okay, I think that's it for today, and I'll see you Wednesday.